Hello ladies and gentlemen, and what I want to do right now is do a proof for the derivative of a power rule. And this one's a hard one. You actually need quite a bit of math to be able to do this one completely. And it's not one I expect you guys to repeat for me, but it is one that I just sort of want you to look at and at least have a reason to believe that it's true for other values of x if I can prove it true for some. So in mathematics, if we can't prove something's true for everything, what we do is we start breaking it up into groups and prove it true for smaller groups of things and then build on that and build on it and build on that. So the level of the math that we have in this course right now, I can prove the derivative rule, the derivative of a power rule, for numbers that go 0, 1, 2, 3, and so on. I can't prove it for other numbers at the moment using the mathematics that you guys have. And even at that, I've got to reach into some mathematics of data management that some of you may have and some of you may not have. So we're going to have to go through this, and I'm only going to prove it. Once again, I'm going to prove it for only values that are 0, 1, 2, 3, all the way up for n values. It is true for all values of the real number system. I'm just not going to be able to prove that. So here's the rule. If f of x equals x to the n, then f prime of x equals x to the n minus 1. And again, I'm only going to prove this for what we call the whole numbers, or the positive integers, if you will. So that my proof's lacking, okay? And no, that doesn't say new. That says n is an element of the whole numbers. So that's what we got here. So proof. What are we going to start with? I'm going to start with the fact that given f of x equals x to the n, and n is an element of the real numbers. So by definition, we're going to say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Nobody can argue with that. We were all here when we developed that. That is what it is. So what is f of x? F of x is x to the n. What is f of x plus h? Well, okay, that'll be x plus h to the n. Take this and put it in for the x's. So therefore, that means that f prime of x is going to equal the limit as h approaches 0 of x plus h to the n minus x to the n over top of h. And that's where things get a little bit tricky, and we need to talk a little bit about some math that you may or may not know from data management. I'll try to be as brief as possible. Let's take a look at x plus h when n equals 0. Well, if that's the case, it's just going to be 1. Let's take a look at what happens when it's x plus h to the 1. It's going to be x plus h. Now, I have another way I could write that. I could write that as x to the 1, h to the 0, plus x to the 0, h to the 1. Now, that seems kind of weird to write it that way, but what it does is it makes these placeholders. And so as x starts at 1 and goes down to 0, h starts at 0 and goes up to 1. So what happens for this one? X plus h squared. We should know that the answer is x squared plus 2xh plus h squared. Now if I write it with this pattern, this descending and ascending pattern, we're going to get x squared h to the 0 plus 2x to the 1 h to the 1 plus x to the 0 h squared. And so again, we see that the 2 and the 0 add up to 2, the 1 and the 1 add up to 2, the 0 and the 2, and we're going x's in descending order and h's in ascending order. And you notice that this number here, 2, is that 2. And what we have here are numbers 1, and it's that 1. Let's look at the next one. X plus h cubed. Now, what this is going to be is it's going to be x plus h times x squared plus 2xh plus h squared. You can expand that out. You're going to get x cubed plus 2x squared h plus x h squared plus x squared h plus 2xh squared plus h cubed. Putting all of that together, we're getting x cubed. Now I've got 2x squared h's, and I got another x squared h, so that's 3x squared h's. I got 1xh squared, I got 2xh squared, so that's 3xh squared, plus h cubed. Now, let's put it in my fancy-dancy little descending and ascending order, and what we're going to get is x to the 3, h to the 0, plus 3x squared, h to the 1, plus 3x to the 1, h squared, plus x0, h3. Notice that this 3 is here. And so if I was to do 4, let's just see the pattern. This is what I'd get. X to the 4, h to the 0, plus x to the 3, h to the 1, and the number in front would be 4. Now I know that the next number in front is 6. You don't know that, but that's okay. And then it's going to be 4, x to the 1, h to the 3, plus x to the 0, h to the 4. So you'll see that we have the descending order and the ascending order, and this number here is that. That's what's important here. So let's take x plus h to the n. So what we know I'm going to start with is x to the n, h to the 0. That's what I'm going to start with. My next number is going to be n, comes down, and it's going to be at times x to the n minus 1 and times h to the 1. All of the rest are going to continue all the way down until I come up with x to the 0, h to the n. And this is what's important to me. And if I rewrite this a little bit with this h to the 0 being 1, it becomes x to the n plus n, x to the n minus 1, h to the 1, plus a whole bunch of other terms all the way down to x to the 0. Let's make that just h to the n. And so what it is a big long string of terms, depending how long n is, where the first term is x to the n, the second term is n, x to the n minus 1 times h to the 1. All the other terms have an h in them. They all have h's. 2 h's, 3 h's, 4 h's, 5 h's, all the way up to n h's. But the important part is they all have h's. And I'm going to stop there, and we're going to take a look how this fits into our proof. So we're going to go back to here, and we're going to look at this. So this is x plus h to the n. So this is going to be the limit as h approaches 0 of, now expanding this, remember what we said that we would have. I would have an x to the n, and then at my next term would be n, x to the n minus 1, h to the 1, a whole bunch of other terms all the way down to h to the n. So this is this. Subtract x to the n all over top of h. So what's important here to realize is that this x to the n and this x to the n are going to cancel each other out, which is going to leave me with a whole bunch of terms with h's in them. I have an h on the bottom. I'm going to common factor an h out of all of these terms. So if I common factor out a single h, this will leave me with n, x to the n minus 1, and this h to the 1 has been common factored out. So it's just a 1. But everyone else is going to have h squared, h cubed, h to the 4. They're just going to go down in a degree of h. They're still going to have h's in them. So I'm going to have a whole bunch of terms that have h's in them all the way down to this one, which is n minus 1. They're just going to have one less h term in them. So once again, all of these terms have an h in them. So we reduce the h's. We apply the limit, bring-di-di-ding, bring-di-di-ding. So as h approaches 0, all of these terms, each one separately is approaching 0, which means they're all approaching 0, which means my final answer is, which is what I set out to prove. So again, that's not a proof I'm going to ask you to reproduce, but I think it's worth going through the argument and seeing where it comes from. And it's not one I'm ever going to test you on. The other ones I will, though. So pay attention to the other ones, and we'll go from here.